Okay, we're gonna start discussing new material for the coming week, and we're gonna be finishing chapter 14, which is on thermodynamics. Excuse me. Okay, so when we ended last week, we ended by just determining the sign of change in entropy, just determining is it positive or negative. Okay, now this week, we're actually going to start solving for the change in entropy mathematically. Okay, so mathematically solving for this change in entropy. So there's a couple nice things. The equation that we're going to use is basically the same equation as for Hess's law. Okay, so no more new equation to learn. Okay, we are going to be using the table of absolute entropies. And this is found on page 437 of your text. Okay, so if you go to page 437, at the bottom is another table similar to the ones that we've been looking at, but this is a table of absolute entropies. Now, let's talk about a few of these things that we're finding. This absolute entropy is abbreviated by using an S, again for entropy, with a little degree sign. Okay, it's measured in joules per mole times Kelvin. For right now, we're not going to worry about this Kelvin. We're going to get to that in the next section. Okay, so just don't stress about this Kelvin right at this moment. Okay, again, because of this degree sign, it means that these are valid. These values in this table are valid at 25 degrees Celsius, okay, which is room temperature. You'll notice on this table that phase is included. Okay, so in the middle column, you'll see H2O gas, H2O liquid. All right, it makes sense if you look at those. Just write them down here quick. Gas and liquid, I'm just taking values from the table. Gas is 188.7. Liquid water is 70.0. Okay, it makes sense that our gas would have more entropy or more disorder than our liquid water. Okay, so these numbers are kind of an indication of, for each of these molecules in their phase, how much disorder there is. Now, no solid, for terms of our calculations, can have a zero entropy, okay? So we're using an absolute zero scale. Okay, and you remember from chapters past, that's why Kelvin comes into play. So we're using this absolute zero scale, and all phases, because of that, all phases will have a value greater than zero. Okay, if you look at this table, you'll notice that there's no zeros and there's no negative values. All right, and one final thing to note is that elements in their natural form, so O2, for example, do have absolute value, or I'm sorry, absolute enthalpy values. Absolute enthalpy value. Okay. So if you remember back to our table on page 424, our standard enthalpies of formation, any element in its natural phase, the standard enthalpy of formation was 0. That is not the case when we're talking about entropy. So even elements in their natural form have an absolute enthalpy value, okay? And so to calculate this delta S, we're going to use the same equation as we did for Hess's law. So our delta S is just going to be basically the sum of our products minus the sum of our reactants. Okay, so let's look at an example. I'm looking at example 14.5. Okay, and I'm on page 436. No, I'm not. No, I'm not. Hold on. Hold on. Getting ahead of myself. I'm looking at example 14.6. And I'm on page 438. Okay, so if you're following along in your book, example 14.6 on page 438. And we want to determine the value of delta S for a reaction. And we're told that the reaction happens at 25 degrees Celsius. Okay, the reaction is one that we've looked at in the past. We have 2 H2O2 aqueous, and that's decomposing into 2 H2O liquid plus 2 oxygen molecules, gaseous, okay? Okay, so remember, we're looking at products minus reactants. Okay, so here are my products, so I'm going to start with those. All right, I have 2 moles of water for my balanced chemical equation. This number here tells us the number of moles. So I have 2 moles, sorry, we're calculating change in entropy. So 2 moles times, well, now I can look at my table on page 437 for my absolute entropy for liquid water. So if I do that, it's in the second column toward the bottom. It's 70.0 joules per mole K. Okay, so here is my water I've taken care of here. I have 2 moles of it times my absolute entropy. Okay, I'm not done summing up my products yet, so I'm going to add my next product. I have 2 moles of oxygen gas. So again, I look at my absolute entropy table because now I'm calculating entropy, and oxygen gas is at the bottom of the second column, 205.0 joules per mole Kelvin. All right, so my products are done. Now I need to subtract my reactants. Well, I only have 1 reactant. So I'm going to subtract my 2 moles of H2O2 aqueous. It's actually at the top of the third column on my table, 143.9 joules per mole Kelvin. Okay, I only have 1 reactant, so I'm done now. Okay, so I added my products, subtracted my reactants. You'll see my moles cancel out. All right, and if I do the math out, let me see here. I get 140.0 joules per K plus, hold on a minute, did I write this equation down wrong? There should not have been a 2 here. I'm so sorry. You guys probably already caught that at home. So this should have been a 1. Okay, So now I just have 1 mole times 205.0 joules per Kelvin. And then finally subtracting 2 times 143.9 is minus 287.8 joules per Kelvin, okay? And if I do all that, then 140 plus the 205 minus 287.8, I end up with a total change in entropy of 57.2 joules Kelvin, joules over Kelvin. Okay. All right, so let's just look at this for a minute. We ended up with a positive change in enthalpy. Okay, is that what we would have expected? So what this is telling me is as this reaction goes, things are becoming more disordered. My entropy or my disorder is increasing. Does that make sense? Well, let's look back at our equation. We had an aqueous reactant that's decomposing into a liquid and a gas. Well, a gas is as disordered as we can become as far as phases go. So yes, it looks like from this equation that based on phases, we would have expected entropy to increase. We can also look at the number of molecules. Here I have 2 molecules in my reactants. In my products, I have 2 plus 1. This is just 1 oxygen molecule. So I have a total of 3 molecules in my products. So again, because my number of molecules is more, I would expect my entropy to increase. And this positive value for my change in entropy proves that. Okay, so just looking at the equation, I would have expected a positive value for my change in entropy. Doing the math, I actually did get a positive value. So that's good, all makes sense. Okay. I think we're pretty much to the last, well, we're not totally to the last section, but this is, we're getting there, we're getting close. We're going to change now and talk about Gibbs free energy. Okay, so way back in the beginning, we started to talk about, or we did talk about how to find, or we talked about what does it mean if a reaction is spontaneous? And it's a spontaneous reaction if once the reaction starts, it keeps going. Okay, and we talked about the fact that like paper burning is actually a spontaneous reaction. Okay, it doesn't happen automatically. I need to light it with a match to give it some heat to get those collisions happening hard and violently enough. But once my paper starts burning, it will keep going. Okay, so spontaneous doesn't mean that it just happens without getting a kickstart. But spontaneous means that once it starts, it's going to keep going. Okay, well, we can use this formula for Gibbs free energy, or this concept, to determine if a reaction is spontaneous or not. Okay, so to be spontaneous, for a reaction to happen and to keep going by itself, a reaction must obey. So to be spontaneous, a reaction must obey the second law of thermodynamics. Okay, if it doesn't obey the second law, the reaction isn't going to happen, because we know things have to obey the second law. So to be spontaneous, to keep going, the reaction must obey the second law of thermodynamics. So to figure this out, we have to look, remember this equation, the change in entropy for a system plus the change in entropy for the surroundings must be greater than or equal to 0. The total change in entropy of these two things, when we add them together, has to show the entropy is increasing or greater than or equal to 0. Okay? So let's think about this. We can calculate how do I want to say this? So we must look, because of this equation, we must look at the system and the surroundings together. Okay? And we've already learned two things that will help us measure what's going on in the system and the surroundings. Looking at the system by itself, we can look at entropy. Okay, and we track entropy with that change in delta S. This is what we've been talking about, okay? If delta S is positive, so if our change in entropy is increasing, it's more disordered. It's becoming more disordered. Our system is becoming more disordered. If our change in S is negative, our system is becoming less disordered. Okay, so our change in entropy actually shows us what's happening in the system. Okay, now let's think about our surroundings. The surroundings we can see what's happening in the surroundings by the change in enthalpy. Because remember, the change in enthalpy is telling us, are the reactants giving off energy or are they absorbing energy? Well, that energy needs to come from somewhere, so it's coming from the surroundings. Okay, so if delta H is negative, what does that tell us? That tells us the reaction is exothermic and energy is being given off. Energy being given to the surroundings. Okay, if our change in H is positive, that tells us we have an endothermic reaction and energy is being absorbed. Absorbed from the surroundings. Okay, so let's see, where do I want to put this? A negative delta H means that the surroundings are becoming more disordered. A positive delta H means energy is being taken away from the surroundings, so I have this wrong. Sorry. When we're giving energy to the surroundings, it's becoming less disordered. And here we're taking energy away from our surroundings, so our surroundings are becoming more ordered. Okay? So I guess what we need to remember here is that if we have to look at the system and the surroundings together. Delta S, the change in entropy, helps us understand what's happening in the system. Delta H, or our change in enthalpy, helps us understand what's happening in the environment. Because with an exothermic reaction, we're giving energy off to the surroundings. In an endothermic reaction, we're taking energy from the surroundings. Okay? So what Gibbs free energy tells us then in Gibbs free energy, we denote with a change in G, which at least this one makes sense. We have G in Gibbs. To calculate our Gibbs free energy, or how much energy is available for use, we take our change in enthalpy and subtract from that our temperature times our change in entropy. And remember I said temperature would come into play later, and here's where it comes into play. Okay, so to calculate the usable energy in a reaction and its surroundings, we use the equation for Gibbs free energy, which is delta G equals our change in enthalpy minus the temperature times our change in entropy. So we already know how to do both of these pieces. We learned this the first week, we learned this last week, the second week, okay? So what we learned first, what we learned later, gives us our equation for Gibbs free energy. Okay, so I want to look at this a little bit more, okay, taking into account what we know here. Okay, so delta G, let me see, how do I want to put this? Let's look at our H and our delta S, okay? We know these can have different values. 1, 2, 3, 4. Okay, and then finally our delta G. Okay, so our delta H, we know, can be negative or positive. In the same way, our delta S can be negative or positive. So here's all the different combinations we can have between our change in enthalpy and our change in entropy. Okay, so let's think about what this means. Remember, we're in our Gibbs free energy equation, we're taking delta H and we're subtracting our delta S. Okay? So if our delta H is negative, what does that mean? Well, a negative delta H means that we're becoming less disordered or more organized. Okay, we're becoming more organized. So whenever we see a negative delta H, the surroundings are becoming more organized. I still have this wrong up here. This is less ordered. Less ordered. I'm sorry. I think I had it written right the first time. Less ordered or more disordered. Okay? So when we have an exothermic reaction, you guys are going to be really confused by the time this is over. I'm sorry, I'm confusing myself, and I hope that when we're done with this and you read the book and do the problems, it will make more sense. When delta H is negative, let's start over. When delta H is negative, it's an exothermic reaction. That means we're giving energy to our surroundings, so our surroundings are becoming less ordered. Okay? When delta H is positive, it's an endothermic reaction. So our surroundings are becoming more ordered. Okay. Let's now look at what's happening when we're calculating our change in entropy of the reaction. So if the change in entropy is positive, that means our entropy is increasing, so it's becoming more or less ordered, less ordered. Okay, so that would be here, less ordered, less ordered. When our change in entropy is negative, that means it's actually becoming more organized. Okay? So it's becoming more ordered. More ordered. Okay, now let's think of our equation. We have a less ordered system. less ordered surroundings, and we're subtracting a more ordered system. So what will our delta G be? We have a negative minus a negative. So this is a negative and a positive. So depending on what the numbers are, we're not sure what delta G will be. Okay. Now we have a less ordered surroundings and a less ordered system. So our delta G is going to be negative and very much less ordered. Okay. Mathematically, we have a negative minus a positive, which will always give us a negative answer. Okay. In this case, we have a positive, a more ordered surrounding, and a less ordered system. So what will happen here? We have a positive minus a negative, so that's going to be two positives. Our delta G has to be positive, and this one will means that things overall are becoming more ordered. And then finally, we have a more ordered surrounding and a less ordered system. So what will the result be? We don't know. Here we have a plus minus a plus. So depending on the numbers, we're not sure if this will be plus or negative. Okay, all of that to say, when delta G is negative, we have a spontaneous reaction. When delta G is positive, we have a non-spontaneous reaction. Okay? So this type of reaction will always be spontaneous when we have a negative delta H and a positive delta S. That, when we plug it into the equation, will give us a negative delta G, and that type of equation or that kind of reaction will always give us a spontaneous reaction. This reaction here will never be spontaneous. The system plus the surroundings plus the system can never become more ordered because of the second law of thermodynamics. It always has to become less ordered. So this will not be spontaneous. This will be spontaneous. These two may or may not be, depending what my numbers are here and how the math works out. Okay? So hopefully that didn't totally confuse anybody, but what you need to remember, bottom line, is if delta G is negative, the reaction is spontaneous. If delta G is positive, the reaction is not spontaneous. Okay, let's look at an example that will hopefully make all of this a little bit more clear. I'm going to write this Gibbs free energy equation up here. We have delta G equals delta H minus temperature times delta S. Okay, so let's look at example 14.7, and I'm on page 440 if you're trying to follow along. And I need to get there in my book. Okay, determine whether or not the following reaction is spontaneous at 25 degrees Celsius. All right, and here's my reaction. I have CO2 gas plus H2 gas yields CO gas plus H2O gas. Okay, so I want to determine if this is a spontaneous reaction or not. I do that by calculating my delta G. That tells me whether it's spontaneous or not. Okay, so the first thing I need for my delta G is I need to calculate my delta H, or the change in enthalpy. Okay, Okay, so now remember, I said all of these equations, H and S and all of them are the products minus the reactants. The only one that's not that way is bond energies, and we're not dealing with bond energies right now. So to calculate the delta H, I can go back in my book and I'm looking for my standard enthalpy of formation table, which is found on page 424. Okay, I can start by looking at my reactant, or my products. I have 1 mole of CO gas. So I look up CO gas in my table, and I find the number beside it is minus 110.5. And my units are kilojoule per mole. Okay, so hopefully you're all with me so far. My other product is H2O gas. Again, 1 mole. I look up H2O gas in my table of standard enthalpies of formation because I'm looking at enthalpy right now. H2O gas, second from the bottom of the middle column, minus 241.8 kilojoules per mole. Okay, so I have my products addressed. Now I'm going to move to my reactants. I'm subtracting my reactants. So I'm subtracting 1 mole of CO2 gas. I looked that up in my table. I see that's negative 393.5 kilojoule per mole. I'm not done because I have another reactant, so negative 1 mole. Okay, if I try to look for H2, I'm not going to find H2 in my table. Why not? Because remember, in enthalpies, when there's an element in its natural phase, its enthalpy of formation is 0. Okay, so I've added my products, I've subtracted my reactants. Okay, so to simplify this, my moles all cancel out, and this whole term goes away because I'm multiplying by 0. Okay, so I end up with 1 times this, gives me minus 100.5 kilojoules, plus 1 times this, well, a plus times a negative actually turns into a negative, so negative 241.8 kilojoules. And then I have a negative times a negative, so this is going to be plus 1 times 393.5. Okay. And if I do all the math out for this, I end up with 41.2 kilojoules. Okay, now I want you to remember enthalpy, we ended up with a kilojoule. Entropy, the units are joules, all right? So I'm going to need to change this to joules so I have the same units. So I multiply this by 1,000. So this is the same as 41,200 joules. Okay, so I just went from kilojoules to joules. All right, so I have my value for change in enthalpy. Now I need to find my value for change in entropy. Okay, so now I need to go to my table of absolute entropies. And that can be found on page 437. Okay, we're going to set up our equation much the same, except our numbers are going to be different because we're looking at a different table. Again, I'm going to start with my products. I have 1 mole of CO gas. So I look for CO gas, I find 197.5. And again, it's joules per mole K. Okay, then I look at my second product. I have 1 mole of H2O gas. Look for H2O gas. I find that in my table, 188.7 joule per mole K. Now I'm going to look at my reactants and I'm going to subtract my reactants. So minus 1 mole CO2 gas. Look in my table. It's in the center column, the second one down, 213.7 kilojoule per mole K. I'm going to subtract my second reactant, 1 mole. Now remember, when we're talking about entropy and absolute entropies, we do have values for elements in their natural state. So I should be able to find H2 gas in the table. And I can, it's in the center column, second from the bottom. The value is 130.6 joules per mole K. Okay. So now I can go do my math. 1 times 1, 197.5. My moles cancel out, so I end up with joule per K. Here I have a plus times a plus. Well, these are all positives, so I'm adding 188.7. My moles cancel out. Joules per Kelvin or per Kelvin. Now I'm subtracting my minus sign. So it's 213.7 joules per Kelvin because my moles cancel out. And then again, subtract out my 130.6 joules per Kelvin because my moles cancel. Okay, and if I do this, I find then my delta S is 41.9 joule per Kelvin. Okay. So now I have my value for delta H, and I have my value for delta S. So I can go back to my equation then, and I'll just rewrite it down here. Delta G equals delta H minus T delta S. So delta G, we can now substitute in our values. Well, delta H is 41,200 joules minus, okay, here's where the temperature comes into play. Now our problem told us that this happened at 25.0 degrees Celsius. 25.0, if you convert that to Kelvin, is 298 Kelvin. So we're going to use Kelvin so that our kelvins ends up canceling out. So 298 Kelvin is my temperature times my delta S. My delta S we found was 41.9 joule over Kelvin. Here's why we had to convert our 25 degrees Celsius to Kelvin, because now my kelvins cancel out. Okay? And my delta G is 41,200 joules minus 12,500 joules. So my final delta G then is 28,700 joules. Okay. The original question is this a spontaneous reaction? Well, delta G is positive, so the reaction is not spontaneous. Okay? So kind of a long problem, but much of it is not new. We're just taking pieces that we've already learned. We've already learned how to calculate enthalpy. We use the standard formation enthalpy of standard formation. We know how to calculate entropy. We use the table of absolute entropies. We had to remember to convert our Celsius to Kelvin. We did that. 25 degrees Celsius is 298 Kelvin. Then it was just plug and chug. We found our value for Gibbs free energy was positive, which tells us that it's not a spontaneous reaction. Okay? When doing your tests, please show me all your work. If I can follow your work, and if you miss something, and if I can find where you went wrong, you'll still get a lot of partial credit. Okay. We're going to move on. And look at example 14.8. Okay. 14.8 is basically a continuation of this example using the same chemical equation. All right. And it says we just calculated delta. Well, let me start out here too. And I'm on page 441, if you're following along. In the previous example, we calculated delta H as 41.2 kilojoules and delta S as 41.9 joules per Kelvin. And this, we're not recalculating Gibbs free energy, but it wants to know for what temperature is the reaction spontaneous. So what temp will make this reaction spontaneous? Okay, so we've just done this example and we've determined that it's not spontaneous, but that was at room temperature. Remember, at this temperature, this reaction is not spontaneous. But if we change the temperature enough, it may become spontaneous. So this question then is asking us, for what temperature would it become spontaneous? Okay, well, it will only become spontaneous. Let's remember our equation for Gibbs free energy. It will only become spontaneous when this is negative. Okay, so another way to say that is if delta H minus temperature times my delta S, the only way it's spontaneous is if this is less than 0. If this value is less than 0 or negative. Okay, well now it becomes fairly straightforward because we already know our delta H, we already know our delta S, so we're just solving this equation for T. Hopefully that makes sense. So let's add T delta S to both sides. Okay, and when we do that, we end up with delta H, these two go away, is less than T delta S. Now let's divide both sides by delta S, and over here we end up with H delta S. Sorry, this is less than T. Okay, we know both of these values, so we can solve for a temperature. Okay, our delta H, now we should address one thing right away. Our delta H is in kilojoules. Remember, we need to convert this to joules so that our units are consistent. So our delta H is 41,200 joules divided by our delta S, which is 41.9 joules per Kelvin. is less than T. Well, here our joules cancel out. We have a denominator and a denominator, which means it moves back up to the numerator. And if we do this math out, we end up with 983 Kelvin less than T. So what this says, if the temperature, if we read it kind of backwards, and the temperature is greater than 983 Kelvin, then the reaction is spontaneous. Okay, so if we get to a high enough temperature, this reaction will become spontaneous. Okay, so hopefully that makes sense to you. Okay, this week you will also be doing experiment 14.2 at home. The only equipment that you need is a rubber band, which I'm hoping that all of you have at home. This experiment shows that this whole Gibbs free energy concept also applies to physical changes. Okay, we've been talking about it in terms of a chemical reaction, but it also applies to physical changes. You will not be writing a full-blown lab report, but I do want you to write a brief paragraph just explaining what happens in the lab. So it's experiment 14.2. It'll be on your homework sheet. Okay, there's one last section we have, and it's kind of a shortcut to this whole Gibbs free energy. If you look on page 444, there is actually a table of standard Gibbs free energy of formation. So it's a shortcut to calculating the Gibbs free energy. And what you will figure out is again, you're going to use a okay, let me back up. So delta G can be calculated using values from the table of standard Gibbs free energies of formation, and it's on page 444. Okay, the abbreviation for the standard Gibbs free energy of formation is a delta G. F, formation, the little degree sign that we're used to now, indicating that it happens at 25 degrees Celsius. The units are in kilojoules per mole, okay? And you can use Hess's law again. Or at least the same equation that we've used for Hess's law, which again is the products minus the reactants. When using this table, the delta G of formation for an element in its natural form equals 0, okay? So just like our standard enthalpies of formation, if an element was in its natural form, the value is 0. It's the same thing for the standard Gibbs free energies of formation. If an element is in its natural form, the value is 0. So let's look at an example. Example 14.9. Okay, and I'm on page 444. Okay, they give us an equation, C6H6 liquid plus 12 waters, liquid, yield, 6 CO2 gas, plus 15 hydrogen gas. Okay. Again, we're going to use an equation just like we used for Hess's law. We're going to start with the products. I have 6 moles of carbon dioxide. So 6 moles. I'm going to look at my standard Gibbs free energy of formation for carbon dioxide gas. I find it in the second column, the second one down, minus 394.4. And it's in kilojoules per mole. Okay, I still am looking at my products. Hydrogen gas. Well, if I look, I'm not going to find hydrogen gas in the table. And that's because hydrogen in nature is found as hydrogen gas. So an element in its natural form, the value is 0. Okay, so I don't need to worry about this. Then I'm going to subtract my reactants. So I have minus 1 mole of C6H6 liquid. That's in the first column, the fourth one down, 124.4 kilojoules per mole. And then finally, I'm going to subtract my water. I have 12 moles, and liquid water is at the bottom of the second column, negative 237.1 kilojoule per mole. Okay. So if I do these out, if you do all this out, I'm just checking my math with my notes here. 24. Yes, you should find that your delta G is 354.4 kilojoules. You'll see the moles all cancel out. Okay, and so would this be spontaneous or not? Well, delta G, my Gibbs free energy, is positive, so it's not spontaneous. Okay. And with that, we are done with chapter 14. At the end of chapter 14, there's a little brief biography about Josiah Willard Gibbs that you can read. It's interesting. Okay, so look online. You will see this week's homework. Well, I guess you had to look already to see this week's homework to get the video links. I want you to notice that a couple things are different. I have assigned the extra problems from the online material. I've given you a link to the online material for the entire chapter. The link to the extra problems can be found at the bottom of that page. I gave you the link to the extra material for the whole chapter because there are some videos in there, and if you're having trouble with anything, you might want to watch some of those videos. So at the bottom of that link is another link that takes you to the extra practice problems, and then there's also a link to the answers. So I want you to work through those this week in addition to finishing up your comprehension checks and your review questions. The second page you will notice on your homework sheet is, believe it or not, I am going to give you a little bit of extra credit. Okay, I've put an assignment out there that's due in 2 weeks. If you want to do it for extra credit, it's worth 5 extra test points. So in the past, what little extra credit I've given has been for homework, so it didn't really amount to much. 5 extra test points could be quite meaningful. So it's up to you whether you want to do it or not. The assignment is basically to write a 3-paragraph essay on one of the scientists that we've studied this year. I think the minimum word count is something like 350. I want you to do it in MLA format. You need to use in-text citations and do a works cited page. And I've told you what belongs in each of the 3 paragraphs. The first paragraph is just some basic facts about the scientist, like his life, his death, where he lived, blah, 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 where he went to school. The second paragraph should outline why he's known in the scientific community, like what did he discover, what did he invent, maybe who were some of his peers, did he win any awards for this, why is he famous for it. And then the third paragraph is just how is it relevant, either how was it relevant to his Christian walk, or how can we make it relevant to our Christian walk, and I want you to cite some scripture reference. So anyway, that's all online, and it's up to you whether to do it or not. It would probably be especially important for people to do it if you're teetering between an A or a B or a B or a C. It could make the difference to bump you up. So I'll leave it up to you, but I know this is a difficult chapter, probably one of the most difficult chapters. It's a lot of material and we're doing it remotely, so there's some things stacked against us. So anyway, that's why I'm giving you the chance to do extra credit. I'm also planning to do, I think, a separate video going over the review for chapter 14. So I know sometimes we did that in class and people acted like it was helpful, so I'm hoping to get that done this week. But anyway, as usual, if you have questions that could benefit the whole class, put them out on Google Classroom, and good luck with this week's work. Let me know if you have any questions. I love you guys and I miss you, and we'll see you soon.